Today we're going to talk about Turing pattern. Now, in nature, we can see patterns everywhere. For example, on leopards, you can see spots on them. Now, at the tip of the tail, you can see the spots sort of turns into stripes, which is very interesting. Today we're going to investigate that. Now, I want you to think of the surface of the leopard as, you just bend it out as a carpet, and we understand it as a 2D surface on which different chemicals react and diffuse and forms a pattern. So today we're going to formalize a model to describe that. Now, the model we have give us these results. We can see that both spots and stripes can form in our model. This is the same model happening on a leopard surface. Now, this model is called the Girard-Menhardt model. We are going to investigate more carefully a 1D version of it. Now, let's take a look at it. U and V. U is the activator, V is the inhibitor. They're two chemicals that are sort of interacting with each other, and the interacting term can be seen at the reaction diffusion equation. It's the chemical reaction part. Now, you're all familiar with the reaction diffusion equation. The only difference is the chemical reaction part. It's different for each model. Now we impose a periodic boundary condition to it, which means that x equal to 0 and x equal to L, both U and V have the same value. Also, we know that if we solve the chemical reaction part, we set it equal to 0, we can solve for the stationary point, which is U and V equal to 1 over B and 1 over B squared. They're both uniform distribution, so that's the stable solution, and that's where we start. Now, there are many characteristics of the Girard-Menhardt model. The first of all is that it spontaneously generate a pattern out of a uniform distribution, which is amazing, which is important. That explains how these patterns are generated, how in nature, because we don't have that many interesting things going on. Basically, it's a uniform distribution with some noise, some white noise added to it. But then, due to the reaction diffusion equation, it actually evolves into something interesting, into something prominent, a stable periodic pattern. Now, the second characteristic of it is that it seems to select certain frequencies of the noise. Now, as you can see in animation, the zero's frequency noise is a mere jerk of the function up or downwards as a whole. Now, this dies down, while on the right hand side it sort of forms a stable periodic pattern. So why? Because on the right the noise is white noise, which contains all frequencies, and since the model selects certain frequencies, the pattern will form because those frequencies gets amplified. Now, the third characteristic is the critical length. This animation is not working, but it's the same animation as the one before. So, as you can see that for the same, the bows start with a uniform distribution with some noise, but on the left it forms a periodic pattern, on the right it doesn't. Why? Well, as you can intuitively see, that maybe you can you think the domain is too small for half the wavelengths to form, so it doesn't have enough room, it doesn't have enough space to fit in one wavelength if if there's some intrinsic wavelength in the problem, and that intuition is right, and we're going to explore it more carefully. Now, let's do some analysis and see, why the model, why this equation has these characteristics. So we start with a uniform distribution, we add some noise, and I want you to think of the noise as a linear combination of of different signals, different frequencies of signals. As white noise, so it's sort of a uniform combination of different frequencies. So we are doing a Fourier series, expanding it as a Fourier series, and the signals with different frequencies behave differently in response to the reaction diffusion equation. Now, the reaction diffusion equation is like radio, which filters certain frequencies, say A0 and A8 frequency decays and becomes nothing, while the A4 frequency grows into, it gets magnified by the radio, and becomes a prominent periodic pattern. Now, if we add them back together, the new noise is going to become a periodic pattern, which is very interesting. Now, if you add that to the uniform distribution, you get a periodic pattern, as we did, as was shown in the different characteristics. Now, to see why some of the frequencies get selected, with more mathematically. First, a mathematical interlude. If we have a linear differential equation, as we did here, we can extract from it a matrix J, that's sort of Jacobian. Now, the most important part of the characteristic of the matrix is its eigenvalues. In this case, there is 5 and this -1. Now, if we know the eigenvalues and eigenvectors, we know how to solve the problem, the linear coupled differential equation, and the solution is in the bottom. The most important part of the solution is that its eigenvalues are on the exponential, so, which means that if the eigenvalue is bigger than 0, no matter the initial condition, it's going to blow up eventually. And if it's less than 0, no matter the initial condition, it's going to decay to nothing. So the eigenvalues of the Jacobian is the key to understand which if the solution is going to blow up or decay, or is going to be filtered or magnified. Now, but what we had is not a linear equation. We have something very ugly. We have a nonlinear part with the reaction part. We have a derivative with respect to x, which is diffusion part. And the way we do with it, I won't go into it in detail, but the way we do this is, first we do a Taylor expansion of the reaction part. We expand it near the stable point. So then this part becomes a Jacobian matrix, a matrix with numbers in each component, not functions, times u and v. So that's a linear part with a Taylor expansion near the stable point. Now, for the diffusion part, we use a Fourier series. We get inspired by our intuition. When we use a Fourier series, we write u and v as a combination of different modes, different frequency modes, and the solution is a combination. Sort of, we separate each mode into the spatial part and the temporal part. The spatial part is sort of a sinusoidal equation, and when we see, if we write it like this, for each mode, the x derivative becomes a I times q, so squared becomes minus q squared, and for v2, So we can see that these two terms become two linear terms. This is a constant times u, constant times v. So now we've turned the whole equation into a linear equation. Remember that we had a periodic boundary condition. So for each the sinusoidal nodes, we have to satisfy the periodic boundary condition, which gives us q equal to discrete values. N takes integers times 2 pi over L. Now, we sort of combine all of this, and we now have a linear equation, differential equation, and we call the matrix J2. But now J2 is a function of Q. As you can see, sort of the diagonal terms have a Q squared in them, and the way we solve the general solution is by solving each sort of the equation for each q, each for uq and vq for each q, because each q's got its own J2 matrix, and then once we've got all that, we combine them together to get u and v. And as you can see here, the u and v is a combination of different modes, and not all of the modes behave the same. For the zeros mode and the ace mode, it decays to nothing, as we've seen. For the force mode, it actually grows into a periodic pattern. Now, as we said, as we did in the linear differential equation analysis, we extracted the two eigenvalues. We say that the eigenvalues are the ones determining if a function is going to blow up or is going to decay into nothing.